Assalamu alaikum everyone. My name is Mohib Sardar and today I'm joined with my friends Heather Hasnain, Hanzla Imran, and today we'll be presenting our topic our presentation on the topic of our discrete project, which is turning cities into networks with Heather, Hanzla and Mohib. Now moving on to the introduction. The main outline of our project this time for discrete structures is to study the price similarities between cities in Pakistan using the consumer price index data that we've been provided. The CPI tracks how prices of goods services change over time, which reflect economic trends between the cities. We will analyze multiple product categories to see which cities have similar price behavior and how they change across the years. We will use the cosine similarity to compare these cities, treating each city as a vector of yearly prices. Cities with similar similar price patterns have higher similarity scores. We will build a network using cities as nodes and our similarities as edges, strong similarities. We will apply graph theoretic tools to identify key cities, clusters, and temporal changes within the economic patterns over the years. After that, we will make the complex price relationship easier to analyze and visualize. Now, moving on to Hansla Imran.
We first learn the normalization. So basically, why was normalization required in the first place? Because, well, a simple example. Suppose you go to the market to buy some oranges. You can buy 1 kg, 2 kg, or maximum of 5 kgs. The price won't be that much. But when you buy meat, 1 kg is approximately 2,700 rupees right now. And that's why comparing these categories as a single unit is not fair. One price is really high while the other price is really low. Hence, here comes the normalization. This is based on the foundation that if we subtract the mean of all the values with the actual value and then divide it by standard deviation, it gives us a small value which we can use to compare with all the other categories, hence making the comparison much fairer. Cosine similarity. Now this forms the basis of how the networks between the cities is being formed. We have a 1 by 7 vector which contains 7 categories of items. We calculate the cosine similarity between between the two vectors, and this basically forms the edge between categories, between years, and between different cities. First of all, after calculating the cosine similarity, these are then converted into the adjacency matrix, and these adjacency matrices basically are what are fed into our actual code where the rest of the operations is performed. The next step was to decide the threshold. In this project, we only compare 0.8 with and 0.7, the centralities and the weighted centralities. First of all, on the centralities, there are four types of centralities which are used in this project: the degree centrality, closeness centrality, betweenness centrality, and finally, eigenvector centrality. Now, we will move on to the weighted centralities. These once again contains four types: the equal, the entropy, correlation, and finally category importance. Let us move on to the code. Here we are on the code. As I've already mentioned, this code is organized in such a way that it contains the folder for actual code, data, which contains the clean final yearly data, monthly data, and the raw data. If you scroll down, you get the yearly data, which contains the normalized and the cosine similarity. This, the cosine similarity is then organized into item-wise and merged. Is in the comprehensive analysis, which basically consists of an entire class by the name of centrality analyzer. Basically, you pass the Excel files, aka the adjacency matrix, to this. It can compute the it first function loads the adjacency data. You can compute the centrality measures, then the weighted centrality. You can already see the formulas. Here they are for equal weighting. As I said, 0.25 assigned to each weight. We got the correlation based weighting. We got the category importance weighting. 0.2 for food staples, etc., leading to 0.10 for clothes, which were assigned at random intervals. And finally, the entropy based weighting. But this code, first of all, we assign once again, we give it the matrix, it calculates all the weighting, and finally it the presents to us the final graphs in the form of heat maps, in the form of visualized in the form of graphs, bars, which we can visualize and learn the relation between different years. That this basically is just an entire class consisting of functions which each have their own unique roles to play, sliders to visualize better. And finally, here is where you pass the Disney files. You can create an instance where you pass the files and it loads it. You can compute the centrality measures, etc.
So now let's move on to the visualization and comparison section. Here we have 5 steps. So here we have the raw graphs visualized. We've got a threshold set of 0.8. We constructed 21 graphs, which corresponds to 3 years and 7 categories. and we did this both with Python and also on paper. So here we have the weighted centrality graph with a threshold of zero point 0.7. This is the year, for the year 2023, and we can see how different cities get different rankings here, depending on which centrality measure we are using. So, for example, for three of these centrality measures, we have Hyderabad on the top, but for the fourth centrality measure, we have Rawalpindi on top, which shows that different centralities correspond to different cities and different rankings on top. Now we can see the subtle changes between the cities and their ranking through the years. This is for the year 2024 with the same threshold, but this time we have different rankings as it shows. So again, we have these subtle shifts in the graph. We cannot show it in extreme detail, but we can say that it is quite obvious from these graphs that there are subtle changes between the rankings of all the cities. So here we have the heat maps. These heat maps, the clusters of these heat maps show how high the similarity between these cities are, which means that if they're red, they are above that certain threshold, which we have set at 0.7. So as you can see, with different categories, we have different clusters being formed based on their similarities. So here we can also see how these clusters can change over the course of years. Here we have different cities having different clusters, and we can also see how cities in a geographical region, for example, in the top left of the graph, you will see that there is a common cluster, and these are the cities of Islamabad and Rawalpindi. So that shows how they correspond geographically as well. And this is the heat map of 2025. Again, we can see the clusters in the top left forming and other clusters as well. So here we have the hash diagrams. This is also a good way of visualizing the temporal relations. As you can see here, for different categories, we have different sort of progression of the hash diagram. In the first two, food staples and grains, and the meat, poultry, and dairy section, we have a full progression, which means that the data and the similarity indexes neatly carry over to the next year. However, for the other five categories, we don't see a clear trend between these 3 years, and we don't see any progression. Okay, so as we can see here, with this data, we can actually compare different cities by year, by categories, and so on. If we adjust these sliders, we can see how the weighted centrality works to differentiate these cities. And as we can see, the score for 2024 is increasing in this in the math scores by year data. So this data is for 0.8 threshold. If you decrease or increase the threshold, the data would be different. As we saw in the slides, we used the 0.7 threshold, and here we have used 0.8 threshold.
Now let's move on to the interpretations of these results. Let's first look on the weighting schemes. As discussed previously, various and different weighting schemes have different impacts on the graphs that we get or the information that we receive. For example, equal weighted graphs highlight well-connected cities, whilst as entropy-based weights emphasize cities with unique influences across categories. Then we also have the threshold effects as well. Higher thresholds create smaller, tighter clusters, whilst lower thresholds produce denser networks with larger clusters, which implies that it's better to use thresholds which are of the higher values so we can get a better analytical data to show our results with. Then we have also the centrality changes. As we saw in the previous graphs, different centralities result in different cities being shown because they work off different measures or metrics. For instance, the degree works on connections, closeness works on central position, and betweenness works on bridging clusters, etc. Changing weights shift city rankings. Then we also have the temporal variance as well. Some cities remain consistently influential over the 2 years. For example, Islamabad and Rawalpindi. And Islamabad should be common because it is the capital city of Pakistan, implying that it has a great economic significance when it comes to the country. Whilst others fluctuate, some cities do fluctuate over time. This shows the dynamic change in the price patterns that we have when it comes to the economic trends.
So to conclude, we find that economic patterns are very related to geography. We saw the relation between Islamabad and Rawalpindi. Centrality also show the importance of larger cities and administrative capitals in the economy running. For example, cities like Karachi, Lahore, Islamabad, and Rawalpindi were quite central. One limitation that we encountered in this project was that the data covered a 3-year period, which might just reflect temporary changes and not very long-lasting trends. However, this project has given us a deeper outlook on network analysis and how to use the data to see bigger trends. Thank you very much.
Okay, before we hop off, we would actually like a short. We made a short video on guidance on how to actually go through the folders and how to actually use the code. Once you open once you have the folder, you will see 5 subfolders: actual codes, the data extraction codes, the graphs, and the utils. Utils are basically small Python files which were used to clean the data. If you can go in here, you can also see the 6 Python files which were used to organize, fill the zeros, and the other good stuff. Now, if we go over to the data extraction code, the same Python file was basically to normalize the prices and to compute those cosine similarity prices. The third folder, which is the graphs, it basically contains all the images for the 21 graphs that we made by hand and using the Python file. Now, if we go over to the actual part, we see in the data that there are multiple subfolders: cleaned, final, networks, processed, and sorted and cleaned and yearly data. From cleaned to the sorted and cleaned, it is basically monthly data, excluding the networks. If you go into the yearly data, it is subdivided into cosine similarity, normalized, organized, and cleaned. Raw is also present if you want to once again use the previous data for something else. If we go over to the networks, which is where the most of the good stuff is happening, there's two subfolders. The one contains the adjacency matrices for the year 2023, 2024, 2025, which is actually divided into two thresholds, point 0.7 and point 0.8. Both contains their own respective Excel files. Now, in the second folder, this is basically where all the code is. To run the code, you have to first load the adjacency Excel files from the point 0.7, point 0.8 threshold folders into this specific folder. Otherwise, the code will not work. This is comprehensive analysis, the code that we already showed in the video, which actually contains the, the base class which we showed you in the video. So that's a small guide on how to use this. Hope you enjoyed it and hope you found it helpful. Thank you and love this.